Share my screen. Yes, 273. So we have first exam on this Thursday, right? It will be offline. So we do this classroom. So it will be 2 p.m. on Thursday. October 7th. October. Let's do 4, 5, 4, 7. 4, 7. 4, 7. Okay, so it will be midterm 1, 2 p.m. on Thursday, on next Thursday, on this Thursday, and it will be on C47, and I will make one more room. I will reserve one more extra room to distribute all of you. You will have at least 4 to 5 meters of the distance. And it will be C47, and see you there. And I will distribute your contribution there. So you can bring one. That's it. Again, no 2 pages. Okay, so I just have a one side of pages now. Okay, any question about the first exam?
Do we need to bring our laptop?
I don't get it.
To bring our computer laptop?
No. Okay, no calculator is needed. No, just hands-on. So the purpose of the exam is not testing your memory ability, but testing your thinking ability. Think about the CSU 373. 373 is not the basic tool, but how you think and how you approach the problem is the key. Then I'm going to ask that as a metric. Okay, any question? No? So exam will be covered before the graphs. So before the graphs. So from the graph, I will cover as a second midterm. Okay. All right, so today's lecture will not be counted as a midterm. Okay, so here. So if you need a special attention, or if you come late or earlier, please let me know ahead. That is fine. You can come earlier, you can come late. That is fine. But please let me know ahead. Okay. So who's not available on show up at 2 p.m. on Thursday? Everybody available. Okay. Who needs to have attention? Nobody? Okay, if you need the attention, please let me know ahead, then I can prepare for that. All right. So today we're going to talk about the graph. What is graph? I assume you heard about the graph, and I assume you know the concept of the graph. Okay, so why is the graph is so important? So if you want to do, okay, I want to do a graph as my PhD program, that is possible. So in a deep learning or basic computer science, there is a guy who focuses on the graph. In a mathematician, there is a team who focuses on the graph. In a computer scientist, there is a team who's only doing a graph. So why graph is so important? Okay, let's talk about that today. So the basic concept of the graphs, the graphs are one of the unifying themes of the computer science, like the sorting. So far we talked about sorting. Now we move on to the graph. Okay, so graph G, vertex, and edges is defined as set of vertex and set of edges, consisting of ordered or unordered pairs of the vertices from B. Okay. So for example, road networks. So we are using our navigation system frequently. If you think about 20 years ago, there was no navigation system. So I remember when I joined the basic military service, so I didn't have a car at that time, and my friend's father, because he went to the basic training together, so his father take both of us to the basic training center. At that time, there was no concept of the navigation. What we do, we use a map. So he wrote down, okay, based on the knowledge. Okay, I take the highway 1 and I exit on that exit 69. From there, take a road something. He wrote it down and he focused on it driving. So now life has changed. So we are focused on the navigation system. And how does the navigation system work? Okay, city to city, point to point, junction to junction. When it starts to bridges, when it starts to divide it into 2 points, then it can be thought of the vertex to edges. Edges are road connecting vertices, right? Then your navigation system can calculate what is the best way to do, what is the fastest way to do, and how can I avoid the accident. That is today's world, right? If you think about the 10 years ago, it wasn't that pretty like this. Okay, if you think about 20 years ago, there was no such thing at all. Because of the electric engineering and computer scientists, engineers and scientists made it possible. And where is the basic fundamental algorithm come from? Graph. Okay, so in modeling road network, the vertices may represent the cities or junctions, and certain pair of which are connected by roads and edges. So Stony Brook is the vertices, Greenport, Orientation, Orient Point, and Shelter Island, Sac Harbor, Montauk, Riverhead, and Iceland. They are the vertices. How they are connected. So this one is 495. This one is I-89, something like this. The road is in edges. So which meaning that I can make navigation system by simplifying real world road to a graph. So by simplifying it, then I can run my algorithm on it. I cannot run my algorithm on real world without assumption, without simplification. So electric circuit. So in an electric circuit with junctions, so as vertices, as a component, as edges. So capacity, this is resistor or resistance. Say this is capacity, this is resistance. And by looking at that, I can calculate how my signals are traveled, how my electric information is delivered. And other graphs, how about social network? So how many of you are friends inside of, let's talk about the Facebook and Instagram. Okay, how many of you are friends on the SNS? Who knows each other? 2, 3? No, you don't want to get involved today? Okay, so say, okay, who has the most friend? Who has more than 1,000 friends? Nobody? Who has more than 500 friends? No? Who has more than 100 friends? I mean the SNS, not real. Okay, maybe 100, right? So I saw one of the student who has more than 5,000 students, 5,000 friends in Facebook. Yeah, she has like, oh, I'm representing this word. Yeah. Accept the every friend's request. Okay, so graphs. So I am, let's say, okay, Taogyong is friend of the Soyoung. Let's assume that if you are not, like even you are not, okay, then everybody can connect it, right? Something like this in an SNS. Some of you, let's say Taogyong is an insider who has many connections. Some of the guy, maybe outsider, okay, let's say anonymous, he has only 2 friends. So what makes it different? Who has many friends has more impact than the others. Agree on it? If I have a 10,000 follower, then I can start to selling it something. Then I can recruit something. Oh, okay, by the way, I have one job opening like a few minutes ago. If you're looking for the translator project, translator meaning that is technical translating. So they are translating low related things. So if you're interested and they are hiring means if you talk to me, you are hired from next day. Okay, if you want to work, there's job opening. Okay, so something like this. So if I am more influential, if I know someone who's a targeting to, I have more values, right? Social networks, so Facebook, some of them has millions of followers. The web, World Wide Web. So everybody start to connect with Google first, then from there they start to their work. Everybody connected Amazon, then from there they start to looking for the cheaper one or the product. So control flow within a main program. So before you're writing program, what do? You start to shoot a program, then how you control the system, right? So how the flow, how your system works, how your code works. And the pairwise similarity within between 2 items. How can I check it? So if I have, let's say iPhone 12 and iPhone 13, let's say Samsung Galaxy Fold. Look at the similarity. So Galaxy, maybe they are using the same CPU. They are similar in the memory. Then by etching them, then I can connect them too. Then I can have 3 components which have a strong or weak or moderate. Then I can find who's more closest, which means if I need to compare millions of things, I can find a similar thing more straightforward, more easily by using graph, right? In a one graph, I have many entities. From there, entity to entity. I'm not directly comparing iPhone to some Samsung Galaxy, but entity to entity. My CPU, my RAM, my speed, my OS, entity to entity. Then I can do in a graphs. The flavor of the graphs. So first step in a given graph problem is determining which flavor of the graph you are dealing with. Okay, so learning to talk. The talk is an important part of walking the walk. Okay, the key word, the fundamental of things. So I need to understand the data first. I need to understand the input data. Then I can find right graph. I can find right flavor. Okay, right flavor meaning I can choose a proper data structure. So flavor of the graph has a big impact on which algorithm are appropriate and efficient. So let's talk about the directed and undirected. I assume you know what is the directed and undirected. So graph, who's not clear about directed and undirected? Everybody clear? Okay, so graph G is a vertex and edge. Undirected, meaning if the edge XY is a part of E, when it is undirected, which means edge YX is also part of the E. Agree? If it is directed, it is not true. Let's see. So X, Y on this direction, it is directed. It is the part of it. Let's say it is a part of my edge. What if this one? It is, of course, in my edge. How about this one? This edge, X and Y. This is part of my edge, set of edges. How about this direction? This is not. Okay. So road networks between cities, big point to big point, it's typically undirected. I agree there, right? How about cities? Cities, inside of cities, there are many one-way roads. In Korea, it is not common, but in US, it is very common. Let's say it is there are many undirected, which means inside of city, there's probably most of the roads are one-directed. Okay, so when we do, let's say you are navigation engineer, navigation architect, you need to understand the character of the city street, character of the highway street. Okay, so most graphs are graph theoretic interest are undirected. Okay, unless specified. So directed are for very rare, but in navigation system, it is in some areas, like the well-developed the city. Those cities are usually directed. So weighted and unweighted. So weighted is more realistic, but in program-wise, unweighted are more straightforward, more easy to compute, right? Say I want to move from, okay, Seoul to Incheon. Let's say this is Songdo. How can I get it? So I may take the highway. I can reach in the cost of 12. But if I go to the local way to local way and local way, it is free, but it takes much higher cost in terms of what? In terms of this weight. What does this weight means? Usually time, right? So if I take the faster way, so in a navigation system, I can choose the fastest or cheapest, or there is also easiest. Easiest means the less time. Okay, so based on that, my graph weight changes. Okay, let's look at the weighted and unweighted again. So in weighted graphs, each edge of the G is assigned as numeric value or weight. So the edges of road networks graph might be weighted with their length and drive time or speed limit, or it is time. And in unweighted graph, there is no cost distinction between various edges and vertices, which means less hop is my best way to do. Okay, so now we understand what is a directed, undirected, and weighted, unweighted. So simple and non-simple graphs. So simple graph is something like we know. Non-simple, oh, they have the cyclic. If you think about real networks and real road system, there is a cycle, there is more complex point, there is maybe some point we cannot expect. Okay, so non-simple is close to reality. Simple is close to theory. And on the simple, it is easier to compute. On the right side, oh, it is more complex. There is more exception I need to handle. Okay, so certain types of edges complicate working with the graphs. A self loop is involving only one vertex. So vertex is edge, and that edge reached me. In a road system, there is a possible. Right, an edge XY is multi-edge if it occurs more than once in the graph. Ah, multi-edge. So any graph which avoids this structure is called a simple. So how about your friendship? Is your friendship is simple? Who's friend of yourself? Okay, my best friend is me. There's some guy like that, right? So friendship is never be easy and never be simple. Well, sometimes he's my best friend, it changes and situation changes. So are you your own friends by definition? Are you? Then I need to see the definition of the friend, right? So just beside. Okay, is the tomato is a vegetable or the fruit? Then like 20 years ago, this was the topic we were like among friends that we discussed heavily. Who think the tomato is the fruit? Who think the tomato is the vegetable? Okay, so how do you know? So tomato, to me, like a fruit. Then why the Western people think it is a vegetable? Then I need to see the definition of the vegetable and the fruit. Definition fruit is I eat it by itself. Vegetable, it become part of the food, right? It usually, right? So if I do the spaghetti, tomato is a vegetable. If I eat the vegetable if I eat the tomato as itself, it could be a fruit, okay? Which means that what I want to say is, okay, I need to see, what do you mean? So are you your own friend? How you define the friend is the key on this question. Walking the walk, talking to talk. What's the important? I need to see that. What do you mean by that? So I see the definition above that, right? So sparse and the graph, the dense graph. So graphs are sparse when only small fraction of the possible number of the vertices are actually have edges. So dense usually connect to everybody. So when we talk about sparse, it is easier to compute because I have a less combination of the computation part. On this case, I have so many things compute. In computation wise, the sparse is way better. Dense, well, I can say I can find 100 ways to reach from Songdo to Seoul. I don't really care there's 100 ways. I only care 2 or 3 candidates, right? So I don't need to compute everything. I want to see the sparse or theoretical and what is recommending. Okay, so in reality, dense is real. But in actual, what I need, I don't want to see the whole information of it. I want to see the one way to get there. Okay, so I can simplify, then compute. Without simplification, oh, I need to compute a lot, which means it's too heavy. I cannot give you the real-time result. Then I simplify the sparse network. Then from there, I give you the recommendation. Okay, so graphs are usually sparse due to the application-specific constraint. So your input need to be simplified. So road network must be sparse because of road junctions. If I have many junctions, I need to simplify it, which means I can discard the more complex route. And typically dense graphs have quadratic number of edges, while sparse has a linear in size, meaning if the input and distance you need to travel is farther and farther, then my computation need to be linear, not need to be quadratic. So if your algorithm can run from Songdo to Seoul, then it should be able to compute the Songdo to Busan. If your runs in the dense algorithm, it cannot handle from Songdo to Busan. It can only handle to Songdo to Seoul, right? So cyclic and acyclic. Acyclic graphs does not contain any cycles. Trees are connected acyclic undirected graphs. So cyclic, if I go to there, oh, I get return to my point, create my cycle. Acycle, it does not create the cycle, does not create the cycle, does not create the cycle. Okay, so we call the DAG, it will be repeating, and it is very important term, directed acyclic graph. It's a DAG, and it is the default term for the graph computation. So DAGs, they arise naturally in scheduling problem. So where directed edge XY indicate they must be occur before Y. So we will see what this DAG means. So in later part, so embedded and topological graphs. Embedded graph, oh, simplified. In topological, in real node look like this. So I don't need to compute all tons in there, right? I only need to simplify. I want to know from Songdo to Seoul. That's it. I don't want to know the left and right and detail all these things. So topological is simplified, and close to theory and easier to computation. So graph is embedded if the vertices and edges have been assigned to geometric position. Is there a drawing of the graph that matters? As in the road and electric circuit networks? It doesn't, right? What I want to know is how fast can I reach Songdo to Seoul? That's what I want to know. How curvy it is, I don't really care. So example, traveling salesperson or shortest path on the point in the plane. Okay, so shortest path. So TSP, traveling salesperson. I want to visit New York, DC, Boston, and many cities. So I assume you heard about TSP, traveling salesperson. No? So let's talk about TSP quickly. What's the TSP? Traveling salesperson. Okay. So let's say I have 7 cities. My goal is starting from my home and visit every cities and return to my home. Okay, that's my goal. So what is most efficient algorithm to do? So my algorithm could be, I started to the closest one, then from there, go to the closest one, 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 from there, go to the closest one. Do you see what I do? Algorithmic way. What is the best algorithmic way to solve the TSP? Say I have this complex algorithm, this complex cities. Traveling salesperson, I need to visit all cities, starting from my home and return to my home. Start and return. What is the best algorithm to do this? Do you understand the TSP? Who's not clear about it? Okay, so solve this with the graph concept we just taught. Okay, so let's discuss let's think about for 2 minutes, and we can discuss together. Ready? How can you solve this? Taegyong, you want to try?
Can you give us some more time because I'm still
Okay,
clicking.
so let's think about for 2 more minutes. So the things what I'm expecting is the algorithm or your approach how to solve this. Ready? Who want to try first? Helen, you want to try?
I'm not sure if this method will work, but I will start with a random edge,
Random
like any
edge.
edge.
So random edge.
Yes.
So I need to start from my home and return to home.
Yes, so I'll
Okay.
pick maybe the closest city from the starting point,
Okay.
and then we'll connect and make an edge.
Mhm.
And since they are connected, I will regard them as a one city.
Okay.
And then I'll have like n-1 vertices, and then I'll
Okay.
continue with that process.
Okay. So heading is introducing a minimum spanning tree. Right. So what's the MST? Who's not clear about the minimum spanning tree? So everybody clear about the minimum spanning tree. Okay. So let's talk about MST first. Minimum spanning tree and shortest path is two different concepts. It looks very similar, but it's two different. How? Minimum spanning tree expanding they're connected. Let's say I have this combination. Minimum spanning tree from, let's say I create this edge. From here, from all my connected, I check my candidates. Then I'm expanding one. Let's say this new expanding. From my connected list, 1, 2, 3. From there, I check every possibility. Then I'm expanding one. So now I have a full member of connected. Okay. So how about shortest path? Shortest path is same example. Shortest path matters my point, my index. From here, I go to here. Then this is the point where it's necessary. Previously, I care about 2 points. Now I only care about this point. More priority care about. Then from here, what do I do? 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 That is shortest path. From here is the minimum spanning tree. Okay, so heading just introduced the minimum spanning tree concept. Okay, go back to the point. Why minimum spanning tree does not work in here? Because if I'm using MST, I come here. From here, I'm checking everybody because I'm assume this one as my one city, which means trebles like this. I need to go to there, return to point, and go to there again. My traveling distance is A. Where am I? My traveling distance is A, B, C. The shortest way, it should be A and D. Do you see? I checked A and B twice because I'm a one person who is doing a shortest path. Starting point, I go to there, check it, sell it, and return to point and visit this city again. Okay, so it is more sophisticatedly, it needs to be covered in the shortest path concept. Thank you, Hadin. Okay, who want to try?
May I try?
Sure.
So first of all, I would make a list that keep tracking of which cities visited or not visited, actually.
Okay.
So as we know, we only have a few edges that we can go, right? Because we can go to only neighbors, right?
Hmm.
So I would try to stretch out like recursively, just tracking all the visited cities, and at the end we're gonna have a few ways that we go through all the cities, and one of them will be the shortest path.
I missed the part. Can you explain one more time?
Oh, so I'm just trying to find a way recursively. I'm basically just brute forcing all the ways.
Working all the way. Okay.
Yes, but the condition is whether the city is visited or not, actually.
Okay.
So if the city is visited, we just exclude the edge, so we can go the other way. And at the end, we're gonna have several ways to reach the source from destination, which is actually same city.
Okay. So Togyong's approach is compute every possible cases. From there, you choose the best cases. Is it right?
That's right.
What's the complexity?
I think it's n factorial, I guess, because
It is n factorial. So factorial wise, I need to compute a lot of things, but in the end, it will give you the final good result, right? If the input is more than 13 city, 13 factorial, your computer cannot handle. 13 cities. 13 cities looks very simple, but 13 factorial, your computer cannot handle. Okay, good approach. Okay, who else want to try? Okay, so can I move on? So if I give you the answer, there is no killer solution on TSP. So what the Dogyong said is the only solution. Okay, Dogyong, good job. Because I cannot guarantee what is right solution before computing everything. Okay, so there is a DP, dynamic program algorithm, which make in linear time search the finding the path. Okay, but still there is many approaches to solve the TSP right way. Okay, so what I want to deliver on the point of this one is, so in actual path, it'll be very complex, but I started from making simplified the cities. Then from cities, I make it to graph and edges, right? Then from there, I make simple problem. So I don't need to compute whole thing, but I make trouble salesperson in a way simpler. Then I compute every possibility. Then from there, I can choose the right way. So TSP in the brute force is not possible to solve it. Therefore, the build-up solution from here. So what is dynamic program? So in this case, what's the difference between brute force and dynamic program? Brute force, from here, I choose every possibility. Okay, then I have many cases. From there, from here, I compute every possibility. Then, do you see how the problems are expanding? That's the brute force. Then it looked like it is not computable, right? Dynamic program. Dynamic program usually builds up the solution. Builds up the solution meaning from here, I started from every possibility. Then on this case, every possibility again. But if this path is computed previously, I'm using them. Say this path was there. I don't need to compute because I know the answer. So dynamic program keep using my computed cache. So if the path will be very complex, but this portion is keep repeating on the other paths, this path, this kind of things will keep repeating. Therefore, I don't need to compute those paths again because I computed once. Okay, that is a build-up based dynamic program, and there is a top-down dynamic program. It will be covered in later lectures. So I hope, and I just give you the taste of the dynamic program. So therefore, if I do the brute force, I build all the trees expanding it. I cannot compute, your memory cannot handle. But you know what? This path was computed before. I don't need to compute again. Okay, by looking at this, okay, from this sub paths that I saw before, I don't need to compute. I'm just borrowing my previous calculation. Okay, therefore I can speed up. Therefore, the factorial computation is feasible on a computer, in a simple computer. So there's a TSP solution as shortest path on pointed in plane by using simplify. The key word is, even in real world, is very complex scenario. What I do is simplify to the point where I can simplify. Then from there, I start to compute my algorithms. Okay. And grid graphs and planar graphs, those looks very complex, but in the end, I can simplify the graph. I can simplify the vertex and edges. Then from there, I can compute very fancy algorithm, which is advanced in the graph algorithm. So let's look at the friendship graph. So consider a graph where the vertices are people and there is an edge between two people if and only if they're a friend. So if and only if they are friends. So Bill Clinton is the house and wife and husband, so they are friends. Obama is friend of the Clinton and Bill Clinton and Hillary. Okay, George Bush is friend of only to Obama. They are the enemy to the Clinton, so they are not. So Donald Trump is the single vertex, has no friend. Okay, so the graph is well defined on any set of these people, Stony Brook, New York of the world, which means I can build up, I can find the connection to the Donald Trump with less than 7 hops. Okay, with this concept of the graph. Okay, so what question might be asked about the friendship graph? If I am thinking you are my friend, and you really think about my friend, which means, okay, I can say, oh, I saw the BTS yesterday and shake their hands. I thought of, oh, BTS is my friend. Is the BTS think I am his friend? No, right? So the definition of the friend, how can you define the definition of the friend? That matters. The connection, edges. Facebook friend, look at the Facebook. I'm a follower of the BTS. Let's say I'm a follower of the BTS. Is the BTS following me? And if even he has connection to me, it's not, right? So the one single graph, if you think about this, the friendship graph, it's not simple. Follower, And we can define the celebrity and the friends and the close friend. They need to be specified. Okay. So if I am your friend, does that mean you are my friend? So a graph is undirected if xy implies yx. Okay, otherwise graph is directed. So friendship is directed. So let's say I have a heard of graph. Heard of graph is directed since countless famous people never heard of me, sadly, right? But I heard about them. I heard about the BTS, I heard about the celebrity, but they never heard about me. They heard of the graph. Okay, how about had conversation with? Is the graph is presumably undirected. I communicate. Let's say I talk to Dong-young. Oh, let's say Dong-young is famous guy. I talk to Dong-young and Dong-young talk to me. Conversation with, by definition, I need to someone who communicate and talk to face. Okay, friendship, I can define it in detail. I can make a heard of friend or had conversation with graph. Okay, I need to understand the data structure more detailed and more sophisticated. So am I linked by some chain of friends to a particular celebrity? Let's say a path is a sequence of edges connecting two vertices. Since Eugene is my father's sister's husband's son, my father's sister's husband's son. Okay. So there's a path between me and him. Let's say Eugene is a famous guy. So if I were trying to impress you with how tight I am with the Eugene, let's say Eugene, let's call the BTS. Let's say RM at BTS. Okay, it's not true. He's not my cousin at all. No. So if I'm trying to impress you guys, impress our 373 classroom. Hey, I'm a friend of the BTS RM. How close you are. Okay, my father's sister's husband's son is the BTS. In detail, I can connect them. So I will be much better to saying that my uncle knew him than to go to into the details of how I connected to them. So thus we often interested in the shortest path between two nodes. So I can directly connect it to the uncle, then he's my uncle's son. Right? So my cousin's son. So I need to particularly understand that. So how can you represent this way to a graph? In graph, it's a family graph. So I can start it from family graph. Me, my sister and brothers, and my father, father/mother. Let's say the mother, my father's sister, all connected, and he is here. RM is. So rather than, am I connected? Hello. Okay. Are you here? Okay. So rather than I go to directed all detailed graphs, I can make my my cousin graph. From cousin's son. In the same contents, I can create more intuitive graphs. Hey, I don't need to build a whole my family structure. Then I can make a cousin graph. Then from there, I can find one direction, one hop from there. So, and it is more intuitive to say that. So they're often interested in the shortest path between two nodes. So I don't need to explain the whole structure of it, then find the shortest meaning point. Then from there, I can start it. Okay, so is there a path of friends between any two people? So graph is connected if there is a path between any two vertices. Okay, by the definition is yes. A directed graph is a strongly connected. Oh, new concept. Strongly connected. If there is a directed path between any two vertices. A notation of the 6th degree of the separation presumes the world social network is graph, connected graph. So do you mean the 6th degree? So if I have a 6 hops, I can connect it to every celebrity in the world. That's the theory of the six degrees. So introduce a strongly connected. If there is a directed path between any two vertices, if I have a 2, then I can say it is strongly connected. So who has the most friend? The degree of the vertex is the number of edges adjacent to it. So how many friends I have? Me to everybody. So number of edges I do have is degree. Say some friends has 1,000 degree. Some friends has a few degree. More degree means I have more friends, more things to compute. Simpler, I have less friends, but I have less things to compute. So what is the largest clique? So social clique is a group of mutual friends who all hang around together. So graph theoretic clique is the clique is right pronunciation, I believe. Clique is a complete subgraph where each vertex pair has an edge between them. So clique are the densest possible subgraphs within the friendship graph. We would expect that the large clique correspond to workplace, neighborhood, religious organization, schools like that. So we are in the Sunni Korea, and we are in CS Sunni Korea. We are in junior, you guys in junior and senior subgroups. So what is in common, the largest one? We can say we are in IGC graphs. You are part of the IGC graph, right? Maybe you can say you are in stay in Korea graphs, stay in Asia graphs. So data structure for graph, I need to explain who's my adjacent, who's my neighbor. So there are two main data structures used to represent the graphs. We assume that graph vertex and edge contains n vertices and m edges. Okay, so graph has n vertices and m edges. We can represent G using m by n matrix. Okay, so where element ij says 1 if ij is an edge of G, or 0 if it doesn't. It may use excessive space for graph with many vertices, relatively few edges. However, can we save space with if one graph is undirected or if the graph is sparse? So look at it in here. So let's say A, B, C, D, they're connected like this. So A, B, C, D, A, B, C, D. I cannot be friend of myself. Therefore, A is connected to B and D. B is connected to A and C, A and C. C is connected to B and D, B and D. D is connected to A and C. This is my M and M by M, M by N matrix. Okay. Can you make, so can we save a space if graph is undirected? Can you save it? Because it is symmetric. As long as it's directed, I need to specify. But if it is undirected, I can ignore the half of it because this connection, meaning this one, I don't need to save a whole lot of energies, right? I can save the half of the space. Agree? How about if the graph is sparse? Can I save it? How can I save it then? So we just solved the first question. Okay, then can you solve this? If the graph is sparse, can you save the sparse? Can you save the space? And how effectively can you reduce the space? Do you understand the point? Who's not clear about the point? Okay, think about for 2 minutes, then let's discuss together. Ready? Who wants to try?
May I just try?
Sure.
I don't know if this works, but I would just eliminate the symmetrics first, and if there's symmetric, I'll just mark them as a 2, just for the sake of that it is undirected. If it doesn't have a symmetric, it means it's directed. So I'm gonna mark it as a 1. There's only one way, and then if there's no way, I would mark as 0, and that's how I save the space.
Can you explain one more time? I think I missed it. So starting from you are eliminating half of them, then?
And then so we can say if there's a symmetric, I'm gonna mark them as a 2 because they're undirected.
2?
Yeah, just the table there is just 0, 1, 0, 1, and 0, 1, right?
Okay. Then you want to say 2?
Yeah, I'll just mark it
Where?
as 2,
Not 1?
not 1.
Okay, so 2, 0, 2, 2, 0, 2. Is that what you
No,
want to do?
only for the symmetrics.
Only for the symmetric.
I mean the only for undirected edges.
Okay. Oh, something like this.
Right.
Okay.
Right.
Okay. Then
And then eliminate the half of the graph, which is the undirected edges.
eliminate the half of it. How can you eliminate half of it when you define a directed?
Wouldn't there be like some edges that we can go back and forth actually? They're actually directed though, but well, in some of the cases we can say it's undirected because you can just go back and forth.
Back and forth. Wow, I don't get it. So anyone who understand the clear point support the Taegyong's comment? No. So I don't get the point that you back and forth. What do you mean back and forth? So 1 is directed, 2 is
Right.
undirected, 0 is not connected.
Yes.
From there, so you want to remove half of it, then it is not possible to eliminate half of it, isn't it? So let's simplify. You are undirected. Okay, let's
So,
simplify. You are undirected. Then
So for the question one, you eliminate the half of the graph in the first,
so
right?
assume that that is a two separate question.
Oh,
Okay, so you are. So we assume you are undirected. So in your case, you can assume whatever you want to. You can start with. You can stick with the directed. You can stick. You want to prefer if you based on your preference. If you want to stick with the directed, you can go ahead. Or undirected, you can explain differently.
oh, I
So
thought
you-
sparse means just directed graph. So
Sparse means directed. So okay, so let's assume the sparse is directed. Okay, from there.
um,
Don't worry. Directed, sparse.
May I ask a question, Professor?
Yeah.
Isn't a sparse graph a graph that like the vertices are connected to only a subset of the other vertices? Like it's not connected to every other vertex. Like it's the opposite of dense graph, right?
So let's assume that let's define the what is sparseness. Sparseness could be directed or undirected.
Right.
Okay. Then
Mhm.
it is of course the subset of the dense graph.
Right. And so isn't it very simple? Like if the sparse graph is undirected, then you can save space the same way that you save space in the first question, because but if the sparse graph is directed, then you cannot save space because you need to keep track of all of the
Okay.
that the opposite is also true. For example, A connected to B doesn't imply that B connected to A.
Okay. So the Fabio is saying if it is undirected, I can save it half. If it is directed, there's no way to save it. Is that what you're saying?
Yes.
Okay, so let's go to extreme. So I can save a lot. Even if it's directed to undirected in a sparse graph. Okay, who wanna try? I love to hear the crazy idea. So when it is sparse, I don't need to maintain matrix, right? In a matrix itself, I need to maintain what's the 0, what is 1. How about list? 2 is connected, this guy and this guy, 3 and 4 and 5. 3, 4. Oh, if it is not connected, I can eliminate them. 4 is connected to 2, and something 6 and 7. With that list representation, I can save a lot of space. That's my intention. So you got the point? So don't need, okay. So the matrix, I need to reserve n by n matrix, initialized to 0. Then from there, I start to fill in 1 when it is connected, directed or undirected. If it is undirected, I can use a 2 like the Dogyeon says. Okay. Then from there, oh, you know what? Rather than using a matrix, by having a list or hash-like tree, 2 is connected 3 and 4 and 5. If it is a sparse, I don't need to maintain a whole lot of things, but I can maintain this short number of edges, a number of vertices, 2, 3, 4, 7, 10, 11, 12, 14 like this. 2 is connected to 4 and 7. 3 is connected to 10, something like this. Then only if I have a connected component, only if I have edges, it will start to expanding. Therefore, if you're comparing the space to this one to this guy, it is a way more efficient. Because in here on the left side, I need to maintain the 14 by 14 and list. And in this case, oh, I can make it very simple. Got it? Can I move on? So something like this. Right? So adjacent list. So adjacent list consists of n by 1 array of pointer, where ith element points to the linked list of the edge instant on the vertex I. To test if ij is in the graph, we search ith list for the j. So it takes big O distance of I, where di is a degree of the ith vertex. So this length is a degree number of edges I connected. Okay, so note that di can be much less than when the graph is sparse, of course. So if necessary, 2 copies of each edges can be linked by a pointer to facilitate deletion. Okay, so when it is connected, when it is directed and undirected, I can represent differently, and I can specify in here. If I need to care about the undirected, if I want to remove 1, I need to go to 1 and remove this guy, and pairwise deletion is necessary when it is undirected. When it is directed, I only delete this guy. Clear? So trade-off between adjacent list and adjacent matrix. Now we know the concept of the matrix and the concept of the matrix. Okay, so faster to test if x and y. Who's the winner?
Matrix.
Existing matrix faster, right? So faster, find the vertex degree.
List.
List is faster. Okay, so less memory on small graph.
List.
Yeah, list is function of n plus n. There's, in the matrix is an n squared function. And less memory on the big graphs. In the big graphs, matrix is more intuitive to see. So edge insertion or deletion, which is more efficient?
Matrix.
Matrix, it takes in 1 time. I can go to that point and update it 0 to 1, and which takes only 1 shot. Okay, faster to traverse the graph.
List.
So list is n plus n. Matrix traverse, I need to go to that point, and go to again. That the computation takes an n squared. So better for most of the problem is the list. Okay. So both representation are very useful and have different properties. Although the adjacent list are probably better for most of the problem. Okay. So edges in adjacent list. So edge has a value, the ID of the edge and the weight And who's my next? Who's my edge node? The graph representation is, it needs to have define the edges and degree. Okay, how many adjacent lists I have, and I can define n vertices and n edges, the number of ID of edge and ID of the vertex, and I can define is it directed or not directed. So degree field counts the number of the meaningful entries for the given vertex. An undirected edge appears twice in an adjacent list. Once the y's in the x's list and x in y's list need to be updated, like we checked in 2 pages before, 2 slides before. So initializing. So I started from everything is a 0. Then from there, I initialize all my degrees to a 0. And all my edges are null. I just initialize that. From there, I can start to update. Okay, so reading a graph. So a typical graph format consists of initial line featuring the number of the vertices and edges in the graph, followed by the listing of the edges at one vertex pair per line. Okay, so scan through, I read all the information. From there, I start to insert to my edges. So inserting edge, I need to make one size of edge by the malloc and define initializing it. Then from there, so I +1 on my degree and update my edges. Then whose goes next? I update this value. Then if it is directed, I don't need to, if it is undirected, then I need to take care of x and y and x. Okay, I need to take care of this one. Then n edges are +1. Okay, this is simple pseudocode in the C format. In a Python, it is a way simpler. You don't need to care about the memories. Okay, so this is it that I prepared today. Any question? Nope. Okay, then you can remain connected if you have a personal question or private question. And see you on Thursday. Thursday is our first midterm day. And good luck. You can bring one sheet of the cheating sheet. Okay, so keyword for the exam is not memorizing. Okay, so how you approach it is the key. All right, guys, thanks for coming today and see you on Thursday. So if you have something to ask, please upload on the Google Classroom that everybody can share. Then I can reply as soon as I can see that. All right, thank you, guys.